And the next part is another question here, and another example. We have a half wave. Before we had a full wave, now we have a half wave rectifier circuit with a ripple change between 7 and 10 volts. So that means that we have the peak value and the minimum value. So we can basically work out the peak to peak value. So the peak voltage is at 10 volts. They say calculate the following: the ripple voltage. So if you had to work out the ripple voltage, is the ripple VDC, the ripple voltage VR. So first is VR, it's 10 minus 7, which is the peak to peak value, gives you 3. Because if this is the maximum value, that's the minimum value. So ripple R peak to peak, you have to work that out first. Okay. And then you can basically work out the VDC. And I didn't ask you to work out the VDC, they just asked you to work out the ripple. So you have to work out the ripple voltage using, oh, I confused them too, sorry. You use the peak to peak and then you put this part here. The second part, that 4.2.2, that second part, the red part, is the answer for the first one. So it's going to be R peak to peak divided by 2 square root of 3. And that gives us the answer of 0.866 volts. Now, if you had to work out the output DC voltage, you're going to use this part of the equation, which is VDC here for 4.2.1, which is VDC is equals to VM minus ripple peak to peak divided by 2, and that will give us 8.5. Okay, this is a half wave, and the question says it's a half wave rectifier. The ripple voltage is that. So there's no capacitors here. You don't hear anything about filtering. So it's basically, it's basically after the rectifier, after the first filter, yes. Percentage of the ripple, it will be after the rectifier, sorry. After the rectifier, percentage of ripple, it will be VR RMS divided by VDC. The values we've worked out, it gives us 10. They always have similar questions. There's not it's just the way they vary the question is that they make sure that you have to find the ripple factor. So they always have to ask us they ask you guys what the RMS value is and what the VDC value is. And that's the most common question they ask with power supply. The other most common question they ask with power supply is for you to draw the diagram. So you have to also learn how to draw the diagram in order to understand what you need to do. Okay, so that's basically what is covered for power supply when it comes to test and stuff that you need to do. Okay, any questions?
Wait, so what's this? They don't draw the diagram. We're gonna have to draw the diagram afterwards.
Yes. Yeah, you draw the diagram for yourself. They don't give you the diagrams for the circuits. So they like to ask you to draw the diagram. They give you of what the power supply has, the components the power supply has, and they want you to draw it. They want to see if you know how to draw it all together. Not a block diagram, a circuit diagram. So you know, I have to know how to draw the rectifiers, the full wave, the half wave, and the center trap. You need to know how to draw the transformer. You also need to know how to draw the filters, the 2 types of filters of the second stage. And you need to also know that the load is always at the end of the circuit. So that's what they always tend to ask you about. Then they ask you a lot about working at the VRMS and the VDC. That's the most common question they like to ask. But the only difference between the other test and every other test is that they ask you in different stages. They want to see if you remember to use different equations for different stages. And the other thing they like to ask is the ripple factor. And sometimes they ask percentage, which means you have to multiply by 100. Sometimes they don't ask you the percentage. So those are the most common questions with power supply.
Okay.
Okay, so now I'm just going to go through semiconductors. use Damlin's semiconductors. This is in week 5 of my class. So this content is only in week 5 of my class, so you can go through them and you can see. And I'm only covering this because it's on the national test, and the national test is on the 15th to the 19th of February. That's when you're going to be writing national test, so you must prepare for that. So the semiconductor diodes, they look like that picture there. They have electronic properties of insulator and conductors. They are basically semiconductors, so at certain temperatures, they behave differently. Sometimes they behave more like inductors, and sometimes they behave more like conductors. So temperature influences it, as you can see. When we have sometimes an increase in temperature, we increase the resistance of the material. And if we increase the resistance of the material, it's basically become more like an insulator, because it's making it hard for current to go through the material. But then some materials, if we increase the temperature, it decreases the resistance. That makes it more like a conductor. So the temperature has a lot to do with the semiconductor's behavior, and also with a lot to do with electricity. That's why Ohm's law only applies when the temperature remains constant. Okay, so the resistance of a conductor increases with an increase in temperature, and in that theory, we put it as a PTC, standing for positive temperature coefficient. So as we increase the temperature, the resistance will increase. Okay, and then for the NTC is a material that has a negative temperature coefficient, meaning that as we increase the temperature, it will decrease the resistance. So there's two types of materials that behave differently with the temperature change. Now, the N-type semiconductor is a semiconductor that's been doped. Basically, they add another type of material to that semiconductor material to change the way in which it works. So what they do is they add an impurity of a pentavalent element. So pentavalent element is basically element that has 5 valence electrons on the outermost shell. So they add that material and they put it with the semiconductor pure material. Silicon is one of an example, and germanium is another example of semiconductor. So they're basically combining those two materials together. The only reason they do this is to modify the semiconductor, to make it more like a PTC or NTC. Remember, PTC stands for positive temperature coefficient, meaning increasing temperature, increasing resistance. And NTC is a negative temperature coefficient, which we increase in temperature, we decrease the resistance. So doping, which is changing the semiconductor with N-type to P-type, is just making it more like one of those two types of material. So the impurity atom is added and it makes a solid crystal. So basically it stabilizes the atom, because remember, in order to have a stable atom, the valence electrons has to all be paired with another atom. Okay, and it has to be the full amount of valence electron in that shell. So let's talk about hydrogen. Hydrogen has one, so it only has one shell. In that one shell, it's supposed to have 2 electrons. So the fact that it only has one means that that whole atom is not stable. So we have to add it with another hydrogen atom in order to make the whole thing strong, if you understand what I mean. So when we're doing impurities, we are making that the whole atoms, the whole element stable, giving it more more electrons and more electrons, so that they can pair up with the valence electrons in the element. So the pentavalent impurities are also known as donors, because they give electrons to the semiconductor, because they have more electrons than they need. Okay, because in their shell, they usually are the second shell, they only need 4 electrons. So they need 6 electrons. So they basically are giving electrons to the other atom in order to complete them. So they can also they have 4, so they can be stabilized in 4, which is because it's better to have on even numbers in an atom there. So doping gives, basically doping is when we add impurity to the semiconductor. Doping gives a smaller number of holes in relation to the number of free electrons. And when we dope with a group 5 element, the result is it results in positively charged circuit. So basically we have more holes than we have electrons. Okay. Any questions?
No, ma'am.
Now the p-type is basically the same. The only thing is that it's trivalent elements that are added, which are the atoms or elements that has free valence electrons on the outermost shell. So the trivalents are added. They are known as the acceptor because they need an electron from the semiconductor. First we had the n-type, which needed electrons from the impurity that is added. Now we have the p-type that needs to take electrons from the, the semiconductor. The doping results in a negatively charged acceptor and positively uh, charged holes. Okay, so we have the p-type and n-type material. So what you would say, the n-type material is has more negatively charged kind of stuff going in there, more free electrons there, looking for a partner there. So we have, I like to say it's more negatively charged. It's more like a conductor. It allows for current to go through it easily. Energy can flow through it. Whereas the p-type one is it's more like an insulator because it's harder for electrons to flow, but it has a lot of valence spaces for electrons to go through it. So what we do is add those two types of materials and put them together. Okay? So we take the 2N and the p-type together and we put it together, but they are joined in a way that is not like electrically done. They're joined in a way that the charges of the two types of material attracts each other and therefore holds the two types of material together. And that in that point there we have the point between the two materials is known as the p-n junction. This p-n junction has a duplication region. That means that it's the place where our electrons goes from a very suffocating area where it has a lot of electrons in it, and it passes through that to go to a place where there's less electrons there. Okay. So this phase where the two material are attracted to each other is known as the diffusion. That's when diffusion takes place. We do not attract the two material by doing anything to it except for the fact that the two charges are attracting to each other and they are making the material come together. And the phenomenon is known as diffusion. The region where we have the p-type and the n-type coming together is known as the p-n junction. It's important to understand that the p-n junction changes according to what is the behavior of electrons flowing through it. Okay, we have a thing that we like to do to the p-n material, and that is biasing. When we bias a material, a component, we are making it more like uh, a switch. Okay, we are deciding whether we want to have it work as an open switch or we want to make it work as a closed switch. So biasing is done when we add a power supply to the material. You can see in the first diagram here, there is no biasing, there is no power supply added. So it's a normal PN material with a normal PN junction and duplication region. Nothing is going on. On the second one, we are doing forward biasing. What that means is that we are putting the positive polarity of the power to the p-type material, and we're connecting the negative type to the n-type material. Okay. So what happens is that the holes in the p-type are moving away from the supply, the p, the p, sorry, it's moving away from the positive charge that's coming from the power supply, because they are the same, charges repulse from each other. So at that point there, we are having the p-type, or the holes, move away, and they're moving closer to the junction, and we having the electrons actually move towards the positive charge. And then on that inside where we connect to the negative, we having the electrons move away from the negative charge from the battery, and they are moving towards the junction. This moving towards the junction is making the junction smaller. So that's why when we forward biasing, we have a small junction. Okay, and you can notice because they are moving both towards the junction, the p type is attracting the electrons from the n type, and they are going through the junction easily with no problem. That is why when we do it forward biasing, we making the semiconductor as if it is a closed switch. Okay, because the current flows easily through that duplication region from one part to the other. And the cycle continues with the electrons. They will go to the p-type, and they will be attracted to the positive charge, and they continue to flow in that manner. Okay, as you can see the diagram, current flow is opposite of electron flow, and in this point the electrons flow in this way, so the current flowing in the electrons is flowing in anti-clockwise, so for the current is flowing in the clockwise direction. I sometimes forget that you guys can't see my mouse. Can you see my mouse?
No.
Okay, so I sometimes forget you can't see the mouse, so you don't know what I'm talking about. Okay, now the
It's
reverse
okay.
bias. Okay. Okay, you must tell me if you can't see it. Sometimes I forget about that. Okay, the reverse biasing is the opposite of the forward biasing. In that we connect the positive polarity to the n type, and we connect the negative polarity to the p type. In that case, the positive holes on the p type are attracted to the negative polarities of the batteries, and the negative electrons are attracted to the positive polarities of the battery. This causes the two parts of the two components in the material p and n type to move away from the junction. So now our junction is getting bigger compared to that of the forward biasing. The junction was smaller, and we are having easy flow of the electrons through the junction. But for this one, it's harder because the junction is bigger. The space between that of the holes and the electrons is so big that we're having trouble for the electrons to flow. The electrons that are going to be flowing there is known as uh, holding current, basically, because it's so little that it actually looks like nothing. It's like micro, you can go down to the micro current. So it's so small. There is a flow there, but it's so small, it looks like nothing. So in that case, this reverse bias connection of biasing circuit makes that semiconductor as if it is an open switch. So you must remember that. The way we connect our polarities to the semiconductors tells us how, whether we have a forward or we have a reverse. And when we have a forward, we have it as if it's a closed switch. And when we have reverse, we have it as if it's an open switch. Okay? The characteristic curves, you can see this is a very important characteristic curves of the diagram of the diode, which is the p-n junction. It's known as a component of the diode. This tells us basically how it behaves. We have the forward biasing stage, which connects the positive to the P and we connect the negative to the N. And this tells us that the current will flow easily. You see there's a positive current, but it's milliamps, but it flows easily. There's a point in which it can break through and start flowing, or it's if we connect it correctly, it will just start flowing. When we come to reverse, you see the value is a microamps. As I said, it is a current flowing, but it's so small that you can't see it, and that's why it looks like nothing is there, and it acts as an open switch. Now, we need to understand there is an equation that we use to basically talk about the current and the relationship between the temperature. Okay, because as I said, they are semiconductor materials and the semiconductor materials are influenced by temperature. So we have to look at the temperature's relationship with the current. And this equation here, which is something we do at N4 that we never did before, is the relationship between the current and the temperature. This I is equals to IS. IS standing for the reverse stationary current. That is the current in basically the current in room temperature. What the current is without being affected by temperature. And the Q is the electron charge value. The Q is the electron charge value, which is a constant. It's always going to be 1.6 times 10 to the power of negative 19. And it's Columbia's as C. We did this calculation somewhere in N1, but it's not too much, but it was with other stuff here. It was electron charge, and this is a constant. That is basically how much charge electrons have. V is the potential difference across the junction in volts. That value is given to you in the equation. And K stands for the Boltzmann's constant, which is 1.38 times 10 to the negative 23 JK. And T stands for the thermodynamic temperature in Kelvin. So if you're given the temperature in Celsius, you have to change it into Kelvin. Okay, I want us to see something quickly. I need to see if I have an example of that equation, then what it will look like, so we can do it. Okay, I have one. Okay, so I'm just going to share my screen and show you an example of that, the calculations. Okay, you can see the screen. So as I was saying about this, the overview of the current and the temperature relationship, we basically have this equation here, and I'm just gonna use an example here. Oh, I didn't put the example there. Sorry, I didn't have the example here. I think I done it in another diagram. So just now, for now, I'm just gonna talk about that part here. The stationary current is basically also known as the dark current. It's basically the value in the without being influenced by anything. So please make sure you make a note of that. Another thing is there's different equation for ideal and non-ideal. For non-ideal, it's basically going to be multiplied by a factor of n. N ideal factor is number is 1 and 2, which typically increases the current decrease. So basically, if we have a different, with non-ideal one, we're going to have n included in the equation. You can see n. I don't know if you can see my arrow. Can you see my arrow?
Yes, ma'am.
Yeah, n is included in the equation there. So that's for the non-ideal part. For the ideal one, it's going to be like that. Okay, so those
Okay.
are the equations when it comes to diodes. Okay, I'm just going to cover this for now, and then I'm going to complete the diodes as we said in the as we said here, semiconductors. Okay, with semiconductors, you have to understand forward and reverse as saturated current, which I just showed you now, and the forward voltage by making use of diode equation, as I showed you now, and the characteristic curve and the application of the junction diode. Then you also need to learn how to calculate, do calculations of forward resistance of the PN junction diode, and then you also need to know how to calculate of current, voltage, and resistance value of the simple voltage regulator with the Zener diode, which we're going to do. Okay, we're going to do that tomorrow, and we're going to go through the characteristics of the tunnel, Vera, and the Zener diode. This is all summary just for the national test, which is on the 15th. And
I can't see anything, ma'am. I think
sorry.
your screen didn't change. Did you change your screen?
Oh yes, I did. Let's just see.
My side it didn't.
Okay, maybe because it's not seen there. Okay, let me just go and share it. Okay, thank you. Okay, sorry.
So what?
Do you see it now?
Yes, it's yeah.
Okay,
I
I
can
had
see
to
it now.
use this one because the other one is not loading up. Um,
Okay.
Weird full screen. So, you semiconductors, what is going to be in the test? Okay, is going to be the calculations of the forward resistance of the PN junction diode. We have to also know the calculations of the current, voltage, and resistance when it comes to voltage regulator. This part we're going to do. Okay, this part we're going to do tomorrow. And the properties and characteristic of the properties, characteristic curves, and application of tunnel, variable, and Verita and Zener diode. That we're doing tomorrow. Today we covered this. We just covered the PN junction. We didn't do the calculation. We'll do it tomorrow. Then we talked about the current, the station current, and the ideal and the non-ideal one. We talked about the current and temperature. Like this one we just did now. So these are all the stuff that's going to be covered for the national test for semiconductor. You must make note of it because there's the stuff you need to focus on to be prepared for the test, which is on the 15th.
Okay, ma'am. Is that test one or it's just a test?
It's just a test, the national test.
Okay. So there's still
Remember,
gonna be test one and test two.
yeah, I believe we're gonna do your national test, and we're also gonna cover uh, We're going to do the DP in a later date, and I'll tell you when we're going to cover that. But for now, you need to focus on what is needed for the national test. All the materials on my class for the national test from week 5 upwards. You need to cover everything from that, from my class, from week 1 to week 5, and you'll be
Okay.
ready for the test.
Okay.
Okay. Okay. Thank you so much for coming to class.
Thank you, ma'am.
Thank you for having me. And I'll see you tomorrow, same time.
Okay, ma'am. Thank you. Enjoy your day.
You too. Bye.
Thanks. Bye.